Hello everyone, I welcome you all in this last session for GATE Preparation 2024 on the subject Power System Analysis. Since we have been discussing the unsymmetrical fault analysis, and we know that this term unsymmetrical defines that the system becomes unbalanced when these faults occur. And these unsymmetrical faults are of three types: single line to ground fault, line to line fault, and double line to ground fault. In the last class, we have discussed the single line to ground fault, that is LG fault, and also solved almost every problems of GATE exam that have been asked till date. And while doing this unsymmetrical fault analysis, basically there are three steps. First step is to find all the three sequence network, positive, negative, and zero sequence network. And the second step is to find the equivalent impedance seen from the fault point or the fault location. And the last step, that is third step, is to find the arrangement of sequence networks based on the fault type. So till now we have seen about the LG fault, that is single line to ground fault. So till now we have seen about the LG fault in which all the sequence networks are connected in series. Since all the sequence networks of current are equal, and also we have derived that the fault current is 3 times of the sequence current. Now in this session, we are going to cover the line to line fault and then double line to ground fault, and also one important topic left, that is we are going to see the how we can find the bus impedance matrix using the Z-bus building algorithm. So let us start today's session. So coming to this line to line fault, this is the second most common fault in the power system, which occurs when two of the conductors come in contact with each other. And here we have assumed phase B and phase C that come in contact with each other, and that causes line to line fault. So here we are going to consider two cases. The first case, like previous one, the first case is without fault impedance, and the second case is with fault impedance. So if we have considered this without fault impedance, then what are the boundary conditions that will help in deriving the symmetrical components of current and symmetrical component of voltage also. So the boundary conditions are, and one important point in the analysis of unsymmetrical fault is that we are assuming that the system is in no load condition. That means IA will be zero before fault occurring. The system is in no load condition. That means no current is flowing through the system. That means phase current A will be zero, and when the fault occurs, this IB is equal to minus IC. And also, since there is no ground involved in this fault, then zero sequence current will be zero. And
Sir,
yes,
sir, why we considered before fault system I1, I2, and I3 equal to 0, sir?
what I didn't get.
Uh,
We are considering no
uh,
load condition
yes, sir. At a no load condition,
because this will simplify about the calculation. Otherwise, it will be very difficult to analyze this fault.
okay, sir.
If we are consider, because if this is no load, if you assume something else, then this will not equal zero, and all the other things will be very difficult to analyze. But
Okay, sir. Okay, sir.
yeah, so this IB is equal to minus IC, and this no ground involved, so zero sequence component current will be zero, and these are short circuited, so VV is equal to VC. Now we are going to find the sequence component of currents. So upon putting the value of IA, IB, IC, IA is equal to 0, IB as it is, IC is equal to minus IV. So you will get IA is equal to 0, since we can also tell without this mathematical expression that since no ground involved, so this,
Sir,
yes,
sir, these current relationships for only for generator or sir or system, sir.
for generator, these are
Okay, sir.
considering a generator
Okay,
sequence.
sir. Okay, sir.
So we will see the for systems also. Like we have, I think we have seen one example in the last class where we have derived the sequence networks for the LG fault. First, we are going to divide all sequence network, positive, negative, zero sequence network, and based on that, we can find the this positive. We can couple this positive, negative, and zero sequence network, and we can find the fault current. So IA1 is equal to this one, and IA2 will be equal to this. So IA1 is equal to minus IA2. So we can say that this positive sequence current is in parallel with negative sequence current, and there is no zero sequence component of current. So yeah, sorry, IA1 equal minus IA2, and also by solving this VV is equal to VC, you can get VA1 is equal to VA2. And so by using these two relation, we can make the equivalent circuit of generator during LL fault without fault impedance. So using this two relation, we can say that this positive and negative sequence networks must be connected in parallel, and there is no zero sequence current because there is no path to ground. Now we have to find the fault current. So fault current is equal to phase V current, and we can derive this phase V current by using the sequence currents. So we have already analyzed the sequence currents, and for IV0 is equal to 0, IV1 we can write lambda square IA1, and IB2 we can write lambda IA2, and we have seen that IA1 is equal to minus IA2. So on putting this IA1 is equal to minus IA2, we get lambda square minus lambda IA1, and lambda square minus lambda is equal to minus j root 3 IA1. So this is very important. Means you have to in many problems they will ask about the what is the magnitude of fault current. So you have to keep this in mind, root 3 times IA1. And if you remember this equivalent circuit of generator, then you can also find the IA1. So I will just tell you, you should remember the fault current magnitude and the equivalent sequence network, means equivalent circuit diagram of generator during different types of faults. Now, in the second case, we will consider the fault impedance ZF. So here we have assumed ZF here. Now the boundary conditions will become I is equal to 0 as the previous case, I is equal to minus IC, that is also previous case, and I0 is equal to 0, that is similar to previous case. This only will change in the when we have considered without fault impedance, there VV is equal to VC, but here this extra term will come IB plus ZF. So VV is equal to VC plus IB plus ZF. So from VV is equal to VC plus ZF IF, you can prove this one, VA1 minus VA2 is equal to ZF IA1. So now similar to this IV is equal to minus IC, we can get IA1 is equal to minus IA2, and we get VA1 is equal to VA2 plus IA1 ZF. So we can make the equivalent circuit diagram of generator. So this will look like this. Both positive sequence voltage and negative sequence voltage will be parallel to each other, and ZF will comes in the between. And the fault current we can derive Fault current we can write in the similar to previous case, root 3 times of IA1, and IA1 magnitude we can write from this equivalent circuit diagram, that is root 3 times of EA divided by Z1 plus Z2, and this sequence network equations we can also write with this equivalent circuit diagram. Now we are going to solve first problem for today's session, that is based on the LL fault. So it is quite a older problem, and that is asked in GATE to 1999. It is of 2 marks, and in that time they are asking subjective type of problems. So here no options and no integer type. So in this problem, the magnitudes of symmetrical components of the current you have to determine when a short circuit occurs between R and biphase wires and the fault current is given as 100 ampere. So let us assume this. Let us assume this three-phase wire and fault is happening between R and bi. So short circuit is happening between this R phase and bi phase. So fault current is IF is equal to IR minus I by. So we can solve this like in conventional way here, because you have to find the symmetrical component of current. So IF is equal to IR is equal to 100 ampere. Therefore, I by will become minus 100 ampere. And what will the magnitude of I be? Can anyone tell? What will the magnitude of I be?
Zero, sir.
Yes, correct. It will be 0 ampere, because we are assuming that no load condition. So applying the expression for finding this sequence component of currents. So it will be 1, 1, 1, 1. Here, what is the expression? Lambda or lambda square? This second row, second column. Anyone remembered?
lambda lambda square
Correct.
lambda square lambda.
Yes, because this will help in the final exam. Because in my student days, I also get confused with this. IR, I by, so IR 0 will be IR plus I by plus IV divided by 3, that will come as 0 ampere. So we have found this IR0. Now we are finding IR1, that is 1 by third of IR plus lambda I by plus lambda square I by IB. So it will become as 1 by third of 100 minus 100 at the angle of 120 degree, and IB 0. So it is like this. So now in the gate exam we don't have this scientific calculator. You have to use different type of calculator. So just bifurcate all these things, like 100 minus, you can write 100 cos 120 minus j 100 sine 120. So you can write 100 divided by 3, 1 minus cos 120. Cos 120 will be minus sine 30. So it will be plus sine 30. Because cos is negative in second quadrant, so negative will come outside, and 90 plus 30, so cos will change to sine, therefore sine 30 minus sine 30. And now sine 120, sine is positive in second quadrant, so sine will just the sine will change to cos, but it will be positive, so minus j cos 30. So put all these values, you will get 100 divided by 3, 1 plus half minus j root 3 by 2. So 100 3 by 2 minus j 3 by 2. So multiplying with this, you will get 50 minus j 28.8675. That is 57.735 minus 30 degree. So here they are asking about the magnitude. So you can write IR1 is equal to 57.735 ampere. So how you can, so we have found this IR1. Now we have to find this IR2. Can we write IR2 is equal to minus IR1? Because we have seen in the previous case,
How, sir?
this IA1 is equal to minus IA2 in the case of LL fault.
Okay, sir.
But I don't think so. Like because you have to use the, because in the previous case we have assumed this phase fault is happening between B and C, and the we are finding this sequence current. So IB1, IC1 will be changed according to lambda. So better to find the in conventional way here, because this phase we are considering is different here. But magnitude will same come same. That is that is sure and short. But angle, for finding angle, it will different. So it will also not take that much time. So you can you can find I1 divided by third IR plus lambda square IB plus IB. So it will be 1 by third of 100 minus 100, 120 minus 120 degree, because lambda square is minus 120 degree, and this is 0. So 1 by third of So take 100 outside, 100 divided by 3, 1 minus j cos 120 degree, sorry, minus j sine 120 degree. So minus sine, so it will positive, plus j sine 120 degree. So again writing it into 100 divided by 3, 1 minus cos 120 degree will be, it will again minus sine 30, so plus sine 30, and this is sine 120 degree will be cos 30. So 100 divided by 3, 1 plus half plus j root 3 by 2. So it will be 50 plus j 28.8675. So it is coming as 57.735 at the angle of 30 degree. So the magnitude sure and short will come as equal 57.735 ampere. So this is quite older problem. Now let us solve this one of the problem that has been asked in GATE 2012. It is of 1 mark. So in this problem they have here what are things given. So the positive, negative and zero sequence impedances of three phase generator are Z1, Z2, Z0 respectively. For a line to line fault with fault impedance ZF, the fault current is KI, where IF is the fault current with zero fault impedance. Okay, here one mistake I did. Sorry, this is IF1 and sorry for this mistake. Now it is good. So they have told you one relation. So it is simple. You have to apply this formula only. So what are things we know? Like for LL fault, I will ask you and just you will tell. For LL fault, if you anyone ask you that what will be the fault current with fault impedance ZF, is IF1. So what is the expression of IF1? It will be
Root 3 E by Z1 plus Z2, sir.
root 3 EA divided by Z1 plus Z2. This ZF here also
3
comes.
ZN. Oh, 3 no, sir. 3 ZF.
No, no, that
Alter current.
that that is the mistake you can do in that is the common mistake. This is LL fault. This is not line to ground fault or double LG fault. Understood?
Oh,
So these three
okay.
times will not come. If you see in LG fault, then it will be 3 ZF. And if you see in LLG fault also, where ground comes into picture, this will become three times. But this is there is no ground involved, so it will be only ZF. Correct.
Okay. Okay, sir.
So this you remember. Here you can see this LL fault. Here this not three ZF times. But for LG fault or LLG fault, this will become three times of,
Yes. Figured it.
yeah,
Nice, sir.
like I will show you this one. For LLG fault, this 3ZF will come, and for
Oh,
LG also. So just be careful. Fault analysis is very easier, but some parts is little bit you have to take care. Otherwise, there will not a problem in GATE exam, and they will ask very silly type of problems in GATE exam from the fault analysis. Fault current with zero fault impedance. That is IF. So IF is equal to root 3 times EA divided by Z1 plus Z2, and it is given that IF1 is equal to KIF. So we have to find the relation of K. We have to find the relation of ZF with other sequence impedances. You have to do nothing. This is given. So just put the expression here. So it is root 3 EA divided by Z1 plus Z2 plus ZF K into root 3 EA. Root 3 will get cancelled out. So you can write Z1 plus Z2 equal to K times Z1 plus Z2 plus K into ZF. So here we can see that Z1 plus Z2 we can take common. So Z1 plus Z2 we can take common, that is 1 minus K is equal to K into ZF. So we can write ZF as Z1 plus Z2 1 minus K divided by K. So correct answer is A. Now we will move to next problem, that is quite a bit little bit looks like very complex, but it is also not that complex. So in this problem, first want to mention the date time. It is asked in GATE 2023, the very recent problem, and it is of 2 marks. So whatever we know about the unsymmetrical fault analysis, they have put all the steps. Like in the unsymmetrical fault analysis, you have to make the all positive sequence network first, and sorry, all sequence network first, and then you have to find the equivalent impedance across the fault point, and then you have to make the equivalent circuit diagram with the help of equivalent impedance and then relations you got from analyzing the fault upon analyzing the different type of faults. Here in this problem, all means all three steps has been covered. So this is a very nice problem. If you understand this problem, then you can means you have built understanding of unsymmetrical fault analysis. So here in this problem, this two bus power system, this is shown over here, has one alternator supplying a synchronous motor load through a star delta transformer. The positive, negative, and zero sequence diagrams of the network are shown in figures second, third, fourth, respectively. So this is good that they have made this positive, negative, and zero sequence network in the question itself. Sometimes they may just give you this all values and they will ask you to make the positive sequence network and you can find this equivalent impedance across the fault point. And this all reactances in the sequence diagrams are in per unit. And here for a bolted line to line fault means that is fault impedance is zero between phases B and C at bus 1. So fault is happening at this bus 1. Neglecting all free fault currents, the magnitude of the fault current from phase B to C in per unit. So what are the first step? First step is to make the sequence network. So sequence network in the question itself it is given. So now the second step we have to find the equivalent impedance of the sequence network, uh, equivalent different positive, negative, zero sequence impedance across the fault point or the fault location. So now we are going to first find the equivalent impedance across the fault point or fault location. So here it is given that LL fault is happening at bus 1. It is given. So at bus 1 it is the important point. Now it doesn't matter that which type of fault is happening. So it is happening at bus 1 that matters. So that will help in finding this equivalent positive, negative and zero sequence impedance. So first we are going to find the positive sequence, equivalent positive sequence impedance. And this is second number bus and this is first number bus. So if the fault is happening at this bus, then you have to find the Z1 equivalent. So Koteswar Anil, can anyone tell what will the Z1 equivalent? If you are finding the equivalent impedance across the
Sir,
yes,
point 2 in parallel with point 3, sir.
Point 2 parallel to 0.3.
yes, very good. So so it will come as J0.12. So this is for positive sequence impedance. Now for negative sequence impedance, they have given the equivalent circuit diagram that is quite they are helpful in this way. And the values are given as J0.1, J0.1 and this is J0.3. So it is also same. J2 equivalent is J0.2 parallel with J0.3. So it will come as J0.12. So this is LL fault. So do we need to find the equivalent impedance zero what zero sequence equivalent impedance?
No, sir.
Yeah, correct. So there is nothing related with this. They're just given to confuse the student. They no need to find this zero sequence equivalent impedance across the fault point A. Now after finding this equivalent impedance, then we can make the equivalent circuit diagram for LL fault. So we have covered a step 2. Now the third step, we have to make the, depending upon the fault type, we have to make the equivalent circuit diagram. So till a step 2 means making the sequence network and finding the equivalent impedance, that is same for all unsymmetrical fault. But this equivalent circuit diagram will change depending upon the type of fault. So here LL fault we are making, so we have just seen how we have to make this equivalent circuit diagram for LL fault. We know that this positive sequence voltage, negative sequence voltage are in parallel with each other. So we have to make like this. So EA Z1 equivalent and ZF is 0 without fault impedance. So there is no role of ZF. And IA1 is equal to minus IA2. So direction will be like this. And this is VA2 and this is VA1. You can, if you remember the fault current value, then you can directly write, but I have, because this is very fundamental problem, so I have solved by a step. You can directly write IF is equal to root 3 IA and IA is equal to IA1 is equal to EA divided by Z1 plus Z2. So IA1 from the equivalent circuit diagram will be EA divided by Z1 equivalent, Z2 equivalent, and EA be assume it as 1 at the angle of 0. So Z1 equivalent both are J0.12. So J0.12 plus J0.12. So it will be coming as minus J4.167 per unit. And we know that fault current is equal to root 3 times of IA1. And we take the magnitude, that will come as 7.21 per unit. So correct answer is 7.21. So this is for LL fault. Generally they prefer, in the GATE exam they ask from the LG fault type. The very less question they have asked from LL fault or double LG double LG fault, double line to ground fault. So now moving to the last, that is the last type of unsymmetrical fault, that is double line to ground fault. So with a double line to ground fault, two line conductors come in contact both with each other and ground, and we will assume these are phases B and C. So as the previous case, we have assumed the phase B and C. Here we have also considered phase B and C. So what are the boundary conditions that will help in finding the sequence component of current? So boundary conditions are I is equal to 0, VV is equal to VC is equal to 0, and then fault current will be equal to IB plus IC, and this will come equal to 3 IA naught. We will see how it is coming 3 IA naught. So here I have written down the derivation also. So this is the proof. IF is equal to 3 IA naught, and the proof is given below. So IB you can write IA0 plus lambda square IA1 plus lambda IA2, and IC you can write IA0 plus lambda IA1 plus lambda square IA2. So lambda square plus lambda you take common, then it will be like here you can write one more step, 2 IA naught plus lambda square plus lambda IA1 plus lambda square plus lambda IA2. So we know that lambda square plus lambda is equal to minus 1. So upon substituting this, you will get minus IA1 minus IA2, and this minus IA1 plus IA2 is equal to minus IA0. So this will give you 3 IA0. So any doubt, Anil, till here?
No, sir.
I think today again this problem will happen. So I am just sending you the one link
Okay, sir.
that will you can join after 1 hour. This link you copy and some paste somewhere. And I think in the last class someone is asking for my mobile number. So you can contact me through WhatsApp. So this is my mobile number. Now continuing to this LLG fault. So now we have to make the equivalent circuit diagram for LLG fault. So how we can make? So we have the boundary condition I is equal to 0. From there we can get that IA1, IA0 plus IA1 plus IA2 is equal to 0. And from the voltage relation we can get this relation. Since VV is equal to VC, so this will give you VA1 is equal to VA2, and VV is equal to VA0 plus lambda square plus lambda VA1. So this will give VA0 minus VA2. So this is nothing but minus 1, because 1 plus lambda square is equal to 0. So from there you can get VA0, VV is equal to VA naught minus VA2, and all the positive, negative, and zero sequence current will be equal to 0. So we can make the equivalent circuit diagram like this. So we have VV is equal to 0. So we can write, so from here we also get VA0 is equal to VA2 is equal to VA1, because from VV is equal to VC we got VA1 is equal to VA2, and from here we will get, since VV is equal to 0, we get VA0 is equal to VA2. That means all sequence voltage in the LLG fault are in parallel. So we can make the equivalent circuit diagram for LLG fault. This all sequence voltage are in parallel to each other, and this IA1, IA2 and IA0 will sum up and will become equal to 0. So now the second case with fault impedance ZF, and here we have taken one fault impedance ZF. So the boundary condition will change. I is equal to 0 and V is equal to VC, that equal to IB plus IC ZF, and you can derive the IB plus I is equal to 3 IA naught. So it is 3 IA naught ZF, and the fault current is 3 IA naught, just as the previous case. Now from the voltage relation, since V is equal to VC, you can tell VA1 is equal to VA2 and VB is equal to VA0 plus lambda square plus lambda VA1. Therefore, this lambda square plus lambda is equal to 1 minus 1, because 1 plus plus lambda square is equal to 0. So we will get VA0 minus VA2, and this VA1 is equal to VA2. Therefore, and VB is equal to ZF into IB plus IC. Since IB plus IC is equal to 3 IA naught, so you can write VA0 minus VA2. So from here is equal to 3 IA naught ZF. Therefore, VA0 minus VA1 is equal to 3 IA naught ZF. So what are the relations we got? The relations we got, VA is equal to VA1 is equal to VA2, and we got VA0 minus VA1 is equal to 3 IA naught ZF, and and IA1 plus IA2 plus IA naught is equal to 0. So these three relations are enough sufficient to make the equivalent circuit diagram during the LLG fault. So with three relations, we have made the equivalent circuit diagram during LLG fault with fault impedance ZF. Now we are going to solve the problems based on the LLG fault. Okay. So it will end in 11 minutes. So we will join by the meeting link that I provided here. So now this problem is okay. So this problem is asked in GATE 2016, and it is of 2 marks and set 1. And here the problem is that 30 MVA 3 phase 50 Hz 13.8 kV star connected synchronous generator has positive negative zero sequence reactances that given here. A reactance Xn connected with neutral of generator and ground. A double line to ground fault takes place. So LLG fault is happening between phase B and C, involving phase B and C with a fault impedance of J 0.1 per unit. The value of Xn in per unit that will limit the positive sequence generator current to 4270 ampere. So here these values are given in actual value. So first we have to convert this in per unit value. So because these are in per unit, so let us first convert this positive sequence generator current in per unit. So for that we have to find the base current. Base current I base. I base will be equal to S base divided by root 3 times of line to line voltage. S base is given as 30 MVA, so 30 cross 10 to the power 6 divided by root 3 into VLL. LL is 13.8 into 10 to the power 3. So this will give you 2200 2255.11 ampere. Now positive sequence generator current is given, that is IA1 actual, IA1 actual, that is given as 4270 ampere. Therefore we can find IA1 per unit, that is IA1 actual divided by I base. 4270 divided by 1255.11, you will get 3.4021 amp per unit. So let us make the equivalent circuit diagram for LLG fault. So for LLG fault, how we are going to make all sequence voltages are in parallel with each other. So this is EA, this is X1, that is 0.15. So, so this is IA1. So this will constitute positive sequence voltage VA1. So now this is negative sequence voltage, negative sequence current IA2, and X2 is equal to 0.15. Now this is zero sequence. X naught is equal to 0.053xn. So this is VA2 and this is VA0. Here in this problem they have also given the fault reactance. So where we are going to make the fault reactance? Here we have to put the fault reactance in the series with X naught of 3xn, or at this between this VA0 and VA2. Anil Koteswar, can you tell
Sir, at a fault point, sir.
where this 3x will be placed? We are making the equivalent circuit diagram. It after the fault impedance means after finding this reactance, then you have to make the equivalent circuit diagram with all sequence networks, with all the equivalent sequence reactance. So I am telling I have to make it here or here 3xf,
That middle, sir, that one. 3x.
top one.
Ah, yes, sir.
Yeah. So don't uh, merge this fault reactance in this VA0. It is separate. So it will be we have to make here 3xf. So because we have seen this relation also, I think. Yes, from here you can get VA0 is equal to VN 3 I naught ZF. That's why it will come. So let us just join the other meeting, all of you. I am closing this session. I am ending this session, join the other meeting. Koteswar Anil, join the other meeting. I am closing this. Yes, good. Now I am sharing the session.
Yes, sir.
Yeah, now I am sharing the slide and we will continue. So we are here. So we have made the equivalent circuit diagram and we have found this IA1 per unit. So IA1 we can write EA divided by x1 plus, so it will be x2 parallel with x0 plus 3xn plus 3xf. So IA1 we got 3.4021. So EA equal 1 divided by 0.15 plus 0.15 parallel with 0.05 plus 0.3 plus 3xn. That is only unknown. So you will get IA1 is equal to, sorry, so take this as left hand side 0.15 parallel with 0.35 plus 3xn equal to 1 divided by 3.4021. So you will get 0.15 plus 0.15 into 0.35 plus 3xn divided by 0.5. 0.15 plus 0.35 equal to 0.05 plus 0.5 plus 3xn equal to 0.2939. Upon expanding this, you will get 0.075 plus 0.45xn plus 0.0525 plus 0.45xn, and on the right side you will get 0.147 plus 0.882xn. So bring xn along the left hand side, you will get 0.082xn equal to 0.01946. So from here you will get xn is equal to 1.07 per unit. So in this problem just notice that they have not directly asked about the fault current. If you have knowledge about this equivalent circuit diagram for the LLG fault, then you can only solve this problem. So that is the thing. You cannot directly apply this fault current is equal to 3Ia0 for LLG fault. So you have to remember the concept also. So the correct answer is 1.07, and the range they have provided is 1.05 to 1.15. Okay, any doubt, Anil or Koteswar?
No, sir.
Yeah. So let us see the summary of about the unbalanced fault. So in unbalanced fault, we have seen three types of fault: single line to ground, LL fault, and double line to ground fault. In single line to ground fault, all the sequence networks are connected in series, and it is parallel to three times of the. So it is connected in parallel to three times of fault impedance if fault impedance is present. And for LL fault, these positive and negative sequence networks are connected in parallel, and zero sequence network is not included since there is no path to ground. And for double LG fault, positive, negative, and zero sequence networks are connected in parallel with the zero sequence network, including three times the fault impedance. So in single line to ground fault, what is the fault current? Can anyone remember? Three times of?
3 by. Okay.
Yeah, correct. 3 EA by
Z1 plus Z2 plus Z0 sir plus 3 Z.
3 ZN, and if fault impedance is present, then it is also 3 ZF. Correct. And for LL fault, it is root.
Root 3 minus the root 3 EA by Z1 plus Z2 sir plus Z.
Yeah, correct. It is very simple. For LL fault, root 3 divided by Z1 plus Z2, and if fault impedance is present, it is ZF only. And for LLG fault, IF is equal to 3 times of IA naught. Correct. There is no formula. You have to just, we know that IB is equal to IF is equal to IB plus IC, that is equal to 3 times of IA0. Correct. We have seen here na, for double LG fault this, and based on the equivalent circuit diagram you can find the currents. So this is the summary. Means single line to diagram, single line to ground fault, you have to remember that all sequence networks are connected in series, and for LL fault, positive and negative sequence networks are connected in parallel, and there is nothing relation with zero sequence network. And for double line to ground fault, all the sequence networks are connected in parallel. That's it. And these are fault currents. That just, if you don't know anything, just remember these things. That will be very helpful in any type of exam. And most important is single line to ground fault. They will prefer this problem more. Now one more problem we have. So here the sequence networks of fault current are as follows. Positive sequence current is given, negative sequence is given, and zero sequence is given. The type of fault in the system you have to tell. So you try yourself. So what do you think? What should be the fault current?
So I think double LG sir.
Yes, very good. Double LG fault. Very nice. Because here we can see that IA1 plus IA2 plus IA0 equal to 0. IA1 is equal to J1.5 minus J0.5 minus J1. That means it is coming as 0. So this case comes in LLG fault only. In LG fault, what happens? IA1 is equal to IA2 is equal to IA0. In error fault, what happens? IA1 plus IA2 equal to 0. There is no zero sequence component current. For LLG fault, we have seen, and for triple LG fault, that is balance fault, that is symmetrical fault. In balance fault, will there negative component of current or zero sequence current will present? Koteswar, Koteswar, can you tell?
Sir,
In balance fault, will this negative sequence current and zero sequence current present?
I sir, your ground is there, no sir.
No, no, balance fault only positive sequence will present
Oh, okay.
because this is balanced na. In balanced, how this negative and zero will come? Zero sequence current will come.
No. Okay, okay, sir.
Only positive sequence component will be there. This negative and zero will be zero, when zero sequence component will be zero, but positive will come into picture because this is a balance fault. Now we have now I think we have covered more or less uh, means unsymmetrical fault analysis very nice way, I think so. If just revise one more time, it will be clear to you. And now moving to the Z-bus building algorithm that is left. So for power system studies, we are carrying out the admittance bus matrix or impedance bus matrix. We are using these two types of matrix, and we have seen this bus admittance matrix in the load flow analysis part. Now for this fault analysis, we may require this Z bus, and this Z bus is preferable over this Y bus in the fault calculation, while in the load flow this Y bus is preferred, because in the load flow there we have to do iterations, and we know that Y-bus matrix is a sparse matrix. So there are more number of zero elements, so that will make the calculation easier. So that's why in load flow we prefer this Y-bus matrix, while in the fault calculation we prefer this Z-bus matrix. So before we see the Z-bus building algorithm, just have some notation. Here Ij we represent as old bus, K represent as new bus, R represent as reference bus, and this Z bus old is the be denoted as the Z bus for older, means before adding this branch impedance, and when we add this branch impedance, this will become Z bus new. So the first modification we are going to do here is that we are adding a branch impedance ZV from a new bus to the reference bus. So that means a new branch is added and the dimension of Z bus goes by 1. Means here dimension of bus will increase by 1. So you can write this KCL and KVL equations. That's Vk is equal to ZVIK, and this will Zki is equal to Zik equal to 0 and Zk is equal to ZV. So the first in the first type modification we are adding the branch impedance from new bus to reference bus. There Z bus new will be So whatever the Z bus you have older, that you write in similar way, and all the other components are 0. Here this is Z bus old, and all the in this column all the component will be 0, just this diagonal elements we have to modify, and this one will also 0. Here this ZB will added. So this will be Z was new for the type 1 modification. Now in the type 2 modification, we are adding we are adding we are adding ZV from a new bus to an old bus. So this means when we are adding a new bus, that means the dimension of Z bus goes by 1. And here this is the equivalent KVL equation. You may write from this given diagram, but the most important thing is that you have to remember this expression. Here again, this dimension of Z bus will increase by 1. So write this Z bus older as it is, but one row and one column will increase. So here you have to write Z1J, and J is the bus number, that is older bus where this bus impedance matrix is added. So Z1J, Z2J, correspondingly ZNJ. Here also Z1J, sorry, ZJ1 it will equal. So Z1 1, Z2, ZJ2, and this is ZJN, and the diagonal component will be ZJJ plus ZV. So this is Z bus new when we are adding a new branch from a new bus to an old bus. Whenever a new bus comes into picture, that means dimension of Z bus will increase by 1. Now the type 3 modification. So here the derivation for type 3 little bit complex and lengthy. So you can, if you want to derive, then you can follow the in textbook. But here I am writing the final expression. So here in the type 3 modification, the dimension of bus matrix will not increase. Why? Because we are adding this branch impedance from an old bus to reference bus. Since there is no involvement of new bus, so the dimension of bus matrix will not change. Impedance matrix will not change. Here in this case, Z bus new will be Z bus old minus 1 divided by ZJJ plus ZB. J means the older bus. And here correspondingly row and columns will be written Z1J to ZNJ, and here ZJ1 JN. This is type 3 modification. And the most complex one is the type 4 modification. Here we are connecting the branch impedance between the two older buses. That means no new loop. That means a new loop is found, but the dimension of ZBUS does not change because there is no involvement of new bus. So here I am again writing the final expression of ZBUS new. ZBUS new is equal to ZBUS old minus 1 divided by ZB plus ZII ZJJ minus 2 ZIJ. So here Z1I Z1J, so ZNI minus ZNJ. So this is subtraction between the older bus, corresponding older bus columns, and here rows will be added. JI1 minus JJ1 correspondingly to JJ. Zin minus Zjn. So this is the new bus. Now let us take one example so you can get understood. So here I am taking one power system having three buses. If you feel any problem while understanding, just ask anytime. We will solve one problem on the Z bus also from the gate. That will be the last slide. This is reference bus J0.1, J0.2, J0.1, and this is J0.25. So this is the bus number 1, this is bus number 2, and this is bus number 3. So Anil Koteswar, can you tell what will be the dimension of Z bus if there are three buses in the system? Can you give
9, sir.
dimension of matrix?
3 by 3.
Yeah, correct. So since 3 cross 3, so it will be. So first step we are adding we are do, doing analysis from the start. A step first is add J0.25 between new bus new bus 1 and reference bus. So this comes under type 1 modification. So here what we'll do, we just add the diagonal elements. So we have older bus is 0 0, nothing is there. So we are having 1 cross 1 matrix. So that constitute of only ZV. So here we are nothing. This we have to find this Z bus for this one. So Z bus will be J0.25. So this is the for the first step. Now second step. Second step is that to add J0.2 between old bus 1 and new bus 2. So here we are adding J0.2 between bus number 1 and bus number 2. That means here the new bus comes into picture. That means dimension of matrix will increase, and this is comes under type 2 modification because we are adding branch impedance from new bus to old bus. So type 2 modification. Okay.
Hello.
Yes,
Sir, why we start from J 0.2
you can start from
in figure, sir?
you can start from other also. You can start from this from two number bus also.
Sir, if you start one and between one and two, then
Then how you will approach one and two that both are uh, new buses. So that is very difficult. So you have to start with a reference bus only.
yes, sir. So it means that, sir, order will be why not 4 cross 4? Sir, reference bus is also present.
No, no, this will be 3 cross 3 because here voltage and current equation will come 3 only because you are
Okay,
writing
sir. Okay,
V1,
sir.
V2, V3, I1, I2, I3, and this
Yes,
voltage,
sir. We should
yeah,
accept reference bus and 1, 2, 3. only.
Hmm. So we know that for Z bus this will look like this. So Z1J, so Z2J. Okay, let us solve fastly. So we know that expression for this one is Z1J ZNJ, and this is ZJ1 to ZJN, and this is ZJJ plus ZV. So we know the older bus, so new bus will be, in older bus we have J0.025. So we write similar J0.25 here and J0.25 here, and we add ZV here. So ZV is 0.2, so it will be J0.45. So here you can write Z22 as ZJJ plus ZV. So ZJJ means 1 1 plus ZV. So J0.25 plus J0.2. Now step 3, step 3 adding J0.1 between old bus and new bus 3. So it will be like this. J0.25, J0.1, J0.2. So 1, 2 and 3. Here it is 2. So this is also type 2 modification like previous case. Type 2 modification. And so if we write Z was new, so like first write the previous bus, old bus, that is J0.25, J0.25, J0.45. So here what we have to write? We are adding bus 1 and bus 3. So bus 1 will be, then row 1 will be replicated, copied. So J0.25 and J0.25 here comes. And in the column also J0.25 and J0.25 will be copied. And Z33 will be ZJJ plus ZBB, ZB. So ZJJ is Z1 plus ZB. Z11 is J0.25 plus J0.1. So it will be J0.35. So till here become. Now we are adding the
Sir,
next. Yes,
sir, in previous diagram, sir, previous slide,
yes.
sir, in last row, first row is copied, sir.
Yeah, in the first last column also first row is copied because we are adding the branch impedance to the older bus. So that's why older bus 1. So
Okay,
that's
sir.
why one bus is copied. Here, this is simple, so it is not that much problem. If we are adding older bus 2 to new bus 3, then this second row and second column will copy to the last row and last columns. That thing you have to.
Okay, sir.
Now step add J0.1 between. Now we have reached the limit 3 cross 3 matrix. So little bit complexity comes because we have to play with older bus only. Add J 0.1 between old bus 3 and and old bus 2. So here this is the case. Yeah, it is correct. So this is the case. Now we have to write the expression for this one. So this
Type
is,
for modification.
yeah, type for modification. Very good. So type for modification. So this is the most complex one. So how we are going to do it? So first let us see type for modification. And so this is the expression. So you have to use this one. So let us see first one. This first we are adding older bus 2 and 3, the branch impedance. So let us find this minus component first. Then we know that older bus. So this will be equal to 1 divided by ZB plus Z22 plus Z33 minus 2Z23, and this is equal to Z12 minus Z13 Z22 minus Z23, and sorry, Z32 minus 33, and here it will be Z2 minus Z31 Z22 minus Z32, and here Z23 minus Z33. Now substitute all the values. So on substituting, you will get J 0.1 plus J 0.45 plus J 0.35 minus J 2.5, and on subtracting two columns you will get 0, J 0.2, J 0.1. Here minus will come 0, J 0.2 minus J 0.1. So if you solve this, then you will get this one matrix 0, 0, 0, 0, J 0.1 minus J 0.2.5, 0 minus J 0.5, J 0.025. So Z was will be write both the matrix J 0.25, J 0.25, J 0.25, J 0.25, minus this one 0, 0, 0, 0, J 0.1 minus J 0.05, 0 minus j 0.05 j 0.025. So we will get finally the z was for this j 0.25 j 0.25 j 0.25 j 0.25 j 0.35 j 0.3. So this one we will got. So now last is that step 5 we are adding the last branch impedance. So adding j 0.25 between old bus 2 and reference bus. So we have half an hour left. So here we are adding the last one, that is adding z 0.5 between old bus and reference bus. So this is type 3 modification. This is type 3 modification. So just solve in the similar way. I am writing the expression because we have less time. So z was new will be. So solve your way. I am writing both the terms j 0.25 and j 0.25 j 0.25 j 0.25, and the minus term we will get here as it is very complex one, j 0.142 j 0.1458 125 0.1458 j 0.2041 j 0.175 j 0.125 j 0.175 0.15. If you simplify this, then you will get the final answer as z was new as j 0.1458 1042 125, and this is j 0.1042 175. This is the final answer. Now, based on this concept, let us solve the one gate problem and then we will wind up today's session. So, this is asked in gate 2003. It is of 2 marks. So, let us see the problem. In this problem, they have told this a 4 cross 4 matrix given for the 4 bus power system, and here a branch having an impedance of j 0.2 ohm is connected to bus 2 and the reference bus. That means we have to do the type third modification. We have to do the type third modification. and then the value of Z22 and Z23 we have to find the newer one. So let us see the solution and see the expression, and we will solve this problem. When is the GATE exam, Koteswar, Anil?
Sir, 11th, sir, 11th February.
11th Feb, sir.
Okay. So here in this problem they ask about Z22 and Z23. Then means we have to only look onto in this. There is no relation with other one. We have to just take care of this one only. Okay. So solution is that in this given that a branch of impedance J 0.2 ohm connected between old bus 2 and the reference. So that means it is type 3 modification. Okay. So let us see type 3 modification. Type 3 modification, this one. We have to use this expression. So it is relation with bus number 2. So in the place of JJ, we will push 2. J means 2 number bus. So it will become Z bus new, Z bus old, that is Z22 plus ZB equal Z12, Z22, Z32, Z42, and this side Z21, Z22, Z23, Z24. Now, so in this problem, we have seen that we have to find the Z22 and Z23. So whatever the element present here, here, we have to do nothing, but we have to do the things with this impedance and J 0.2586, this impedance. Otherwise, we have to don't care about these elements. Correct. And it will be minus of 1 divided by Z 0.3408 plus J 0.2. So inside it will come J 0.3408 whole square, and this term will be, I'm writing directly. So this term will come as minus of 0.116, and this term will come as minus of 0.088. So now if you solve this, then you will get Z22 new as This term J 0.3408 minus of J 0.2147. So this will be coming at J 0.1260 and J23 new will come as J 0.2586 minus J 0.1629. So it is coming approximately at J 0.0956. So if you see the options, then B option is coming as correct. Any doubt, Anil or Koteswar?
No, sir.
So this is for all for this session. All of all the best for your final gate exam and do the best. Don't afraid too much. Just keep calm and do all means what
Sir,
you
this
can do.
topic is important, sir.
Jet was
Yes, sir. That was
not that
all
much
good.
important, I think, but is some how I covered it because many of you may think it has not been covered for the Fortnite. This is not covered. They have not asked many questions.
Oh, okay, okay.
But just if you know the concept now, if you don't know this type 1, type 2, type 3, type for modification, but if you somehow once read, then may you can attempt in the gate exam because solving a problem and learning the things is quite different. Sometimes you may solve the problems based on the theory you covered in the BTech class or somewhere else. You don't just like that.
Yes, sir.
They have not asked the question, I think. I think one problem they more asked in GATE 2013 and before that, and they have not asked from the JEDBUS. But this is quite important for, I think, university exam. They prepare from this JEDBUS. Anil, any doubt?
Okay.
No doubt, sir.
Okay, Koteswar Anil, hope we will meet sometime. Anil, you are
Thank
from
you, sir.
which place?
Sir, I am from Ujjain, sir.
Okay, Ujjain. Nice. You are studying in a state engineering college or some?
Uh, yes, sir. Ujjain Engineering College, State Government College it is.
Okay. You are from MP or somewhere else?
Sir, from MP, sir. I am
Okay.
from Khandwa and I study in Ujjain.
Okay. Okay. Once I interacted with Koteswar, but I have not interacted with you. Okay, Anil, I have shared the
Okay,
number
sir.
also. If you have any means personally doubt or anything, you have to ask me. You can WhatsApp me.
Okay, sir.
Okay, bye bye.
Thank you, sir.
Mm,
Thank you, sir.
welcome, welcome.